Prefabricated bridge sections were assembled in Yokohama and transported by barge up the Tama River. To install the 1,900-ton, 132-meter-long central span, riverbed dredging was conducted. The new span was lifted by a 3,000-ton crane and installed using slide-in techniques. The old bridge was later shifted upstream by 30 meters and dismantled. Additional spans were installed between existing girders, followed by welding and bolting. Expansion joints, anti-drop devices, and pavement were completed post-slide. Final steps included installing lighting, cables, and conducting inspections. The entire process concluded with safety checks and road reopening on schedule. Metal is recovered from the ocean floor by locating lost anchors using sonar, then deploying divers or remotely operated vehicles to attach lifting gear. The anchor chain is gradually retrieved using the windlass system, ensuring brake control and safety checks on components like shackles and swivel pins before hauling the anchor back on board for recycling. The construction of the 1915 Kanakali Bridge, spanning the Dardanelles Strait, commenced in 2017 with detailed geotechnical surveys and seabed preparations. Giant steel caissons, each weighing over 66,000 tons, were fabricated and floated to position using tugboats, then submerged and anchored onto the seabed using precision GPS systems. These formed the foundations for the 334-meter high steel towers. Tower erection progressed in modular steel segments, lifted by floating cranes and bolted using high-strength tension control bolts. Once the towers reached full height, the aerial spinning of the main suspension cables began. Thousands of individual galvanized steel wires were looped across the span using pilot lines and bundled into 144 strands per cable, then compacted and wrapped for corrosion protection. Cable saddle systems were installed atop the towers to support the vertical suspenders, which were connected to prefabricated steel deck segments. Each deck segment, weighing up to 700 tons, was lifted into place via strand jacking from barges and precisely aligned to ensure aerodynamic continuity in the twin-box girder system. Simultaneously, the side spans and approach viaducts were constructed using incremental launching and balanced cantilever techniques. Wind tunnel testing informed the aerodynamic design, while seismic isolation bearings and dampers enhanced earthquake resilience. The structure also incorporated a structural health monitoring system and long-term corrosion protection measures. Blocks are stacked, cut to fit, aligned plumb, rebar inserted, concrete poured into cores, surfaces finished directly without lath, no vibration or bracing needed. The process of working with Yutong aerated concrete blocks using thin bed mortar involves precise steps to ensure masonry. Begin by preparing the foundation with a bitumen membrane to provide a waterproof base. Mix normal mortar according to manufacturer specifications and apply it to the bitumen membrane to form the bedding for the first layer. Place the corner block on this mortar bed, using a rubber hammer and spirit level to align it accurately in height and position. A laser measuring device can assist in verifying the corner block's height. Secure a masonry cord with a nail along the corner block to guide the alignment of subsequent blocks in the first layer. Adjust any height differences using the normal mortar, ensuring all blocks are level and aligned. For the thin bed mortar, mix it as per the manufacturer's instructions, adhering strictly to the specified water quantity. Allow the mortar to rest for 5 minutes, then stir it again to achieve optimal consistency. Apply the thin bed mortar with a trowel or mortar sledge to the bed joints of the first layer, maintaining a thickness of approximately 1 millimeter. In the corner areas, mortar the vertical joints to enhance bonding. This can also be done across the entire first layer for added stability. Continue setting blocks, aligning them with a spirit level and rubber hammer, and remove excess mortar with a trowel. If custom cuts are needed, use a porous concrete saw or bandsaw to shape the blocks, marking cut lines with a pencil and sawing out missing grooves to avoid mortaring vertical joints. For the second layer, apply a horizontal sealing layer using a sealing slurry, following manufacturer guidelines. Prime the blocks with 1 coat, then apply 2 additional coats, allowing each to cure. If required, fill grip pockets with mortar, or use flexible sealing slurry, coordinating with the planner. Apply sealing slurry to the lower 10 centimeters of blocks in the inner corner to prevent water absorption. Start the second layer at the corner, ensuring a minimum bond length of 0.4 times the block height, approximately 10 centimeters. Apply thin bed mortar thinly, 1 to 2 millimeters to bed joints for 2 to 3 blocks at a time. Insert masonry connectors in each layer, alongside vertical joint mortaring for optimal execution quality. Align the corner block precisely, resetting the masonry cord to maintain wall alignment, especially around openings like floor-to-ceiling windows. For openings, maintain the bond length at corners and jambs. Use the masonry cord layer by layer to ensure accurate alignment. Smooth any unevenness with a plane or sanding board. Once the desired wall height is reached, apply thin bed mortar to both bed and vertical joints. Then install lintels into pre-prepared yutong blocks, adjusting their position with a rubber hammer. Mortar both bed and vertical joints during over-masonry. Sand the top block edge to prevent chipping when placing the ceiling. Cover the wall crown and open jambs with foil to protect against moisture. Address minor imperfections with Yutong filler mortar and smooth surfaces with a sanding board for a uniform finish. The External Thermal Insulation Composite System, ETICS or SETA, using multi-pore panels by Yutong, offers a modern, effective, and environmentally friendly solution for improving thermal performance and structural durability in both new buildings and renovation projects. Among its key advantages, multi-pore is breathable, allowing moisture within the wall to be properly managed. Fire-resistant, non-combustible, ensuring passive fire protection. And inert, meaning it is immune to mold, insects, and other pests. Additionally, because it contains no harmful fibers and emits no toxic substances, it is a safe and ecological choice. The installation process is divided into 8 clear steps. Step 1 involves gathering all necessary materials and tools, including lightweight and filling mortars, reinforcement mesh, spirit level, trowels, power drill with mixing paddle, anchor dowels, ceiling tapes, starter and edge profiles, multi-pore mineral insulation boards, finishing plasters, and EPS base insulation panels. In step 2, surface preparation is critical. The substrate must be clean, dry, even, and structurally sound. Any dust, algae, efflorescence, or loose particles are removed using brushes, pressure washers, or grinding tools. Weak or chalky surfaces should be primed accordingly. Any damaged or damp areas must be repaired before proceeding. If no base insulation is used, a metal starter track is fixed to the wall as the lower system edge using dowels. In areas exposed to ground moisture or splashing water, typically up to 30 centimeters above grade, EPS baseboards are bonded with multi-pore SSK waterproof adhesive, which is mixed 1-to-1 with cement. These panels are then mechanically fixed with 2 dowels per panel and coated for protection. Step 3 involves the application of the multi-pore insulation boards. The lightweight mortar is applied using a notched trowel in the opposite direction to the placement to ensure proper adhesion. The panels are installed horizontally with tight joints and staggered to avoid cross joints, maintaining a minimum offset of 15 centimeters between rows. At windows and door reveals, the boards must be cut precisely. Pre-compressed ceiling tapes, corner mesh profiles, and reveal boards ensure a tight and crack-free connection. In step 4, adjustments are made to accommodate fixtures such as electrical boxes and conduits. Accurate cuts allow the boards to fit snugly around installations. Mechanical fixings, plate dowels, are added in step 5. The number of dowels depends on the project specifics. For single-family homes, 1 dowel per board is typically sufficient. Dowels can be surface-mounted or countersunk, the latter being sealed with multi-pore filler mortar, which can also repair minor board damage. Step 6 is the reinforcement layer. Using a 10 mm notched trowel, the lightweight mortar is spread over the surface, embedding the reinforcement mesh into the top third of the mortar layer. At corners of windows and doors, diagonal mesh pieces are applied to prevent cracking. In the base zone, the same SSK waterproof adhesive is used to reinforce the lower portion of the facade for added moisture protection. Step 7 covers the finish coating, where a thin layer mineral render is applied and textured according to the grain size. This coating protects the facade against weathering, mechanical stress, and biological growth, ensuring a durable and aesthetically pleasing finish. A variety of color and texture options are available, depending on design preferences. Step 8 includes additional measures, such as installing house numbers, mailboxes, or exterior lighting. For this, spiral anchors are used to ensure thermal bridge-free attachment. Detailed design guidelines and structural solutions are available in Multi-Pore's technical manuals and website. Overall, the Multi-Pore, ETICS system is a sustainable, fire-safe, impact-resistant, and algae-free thermal insulation solution. It is particularly well-suited for both new constructions and energy-efficient renovations, offering long-term performance, ease of installation, and environmental benefits in one comprehensive package. Monolithic domes are constructed following a method that requires a tough, inflatable airform, steel-reinforced concrete, and a polyurethane foam insulation. The construction of a monolithic dome begins with site preparation, followed by forming a circular concrete ring foundation, reinforced with steel rebar. Vertical rebar is embedded into the ring to later connect with the dome's structural reinforcement. Depending on the design, the floor is either poured with the foundation Next, a double-door airlock is installed to allow safe entry into the pressurized structure. Then, the airform custom fabricated to the exact dimensions of the dome is securely attached to the ring beam and inflated using blower fans. These fans maintain constant air pressure throughout the construction. Once inflated, approximately 3 inches of polyurethane foam is sprayed onto the inner surface of the airform. This foam layer provides insulation and forms a base for attaching the steel reinforcement. Rebar is placed over the foam in a grid pattern, using horizontal hoop and vertical bars. The spacing and diameter of the bars vary depending on the size of the dome, with larger domes requiring denser reinforcement. After the rebar is in place, Shotcrete, a high-strength sprayable concrete mix, is applied in layers to the interior surface, embedding the steel rebar and forming the structural shell. The concrete mixture is carefully calibrated, and the application continues until a 3-inch thick shell is achieved. Once the concrete is set, workers manually trowel the surface to smooth imperfections and remove any rebound material. The blower fans are turned off after the structure is self-supporting. Lastly, a protective polyurethane coating is sprayed around the exterior base, and the interior is painted, completing the monolithic dome construction. The extraction process of quartzite flagstone begins with positioning a hydraulic excavator, 32 to 40 tons, equipped with the eccentric ripper XR40 at the quarry site. The attachment operates at a working hydraulic pressure of up to 300 bars MPa and a flow rate of 200 L per minute. The operator aligns the ripper's tooth against natural seams in the quartzite formation. Once activated, it uses high-frequency vibrations up to 1,200 blows per minute to fracture the stone efficiently without the need for explosives. The ripper's internal mechanism, driven by hydraulic pressure and supported by an accumulator charged to 60 bars, generates intense percussive force. With a mass of approximately 4,200 kilograms, including the top bracket, the attachment penetrates and loosens the quartzite layers, separating large flagstone slabs with minimal fragmentation. The excavator then lifts and moves these slabs aside for further processing. Throughout operation, the case drain pressure is kept below 5 bars to protect hydraulic components. The XR40's compact dimensions, 3,100 by 900 by 1,840 millimeters, and robust design allow precise maneuvering in tight quarry environments. This method ensures a safer, more controlled, and environmentally friendly extraction process compared to traditional blasting techniques. Excavation reached 20 meters deep, followed by final rock blasting, joint treatment, reinforcement, and concrete pouring for the lower base mat. Anti-seismic bearings were installed, then seismic pads and 18 support columns were added to build the reinforced concrete tokamak structure. The stone quarrying process has undergone significant technological advancement. Initially, workers used compressed air drills, wedges, and shims to extract stone. This evolved into jet burning, controlled blasting, and drift methods. However, the introduction of diamond wire technology revolutionized the process. This method employs a steel core embedded with diamond beads, which are rotated and pulled through the stone using motors and pulleys. The diamond beads perform the cutting, enabling precise and efficient extraction. Quarry layouts have changed as well, shifting from derrick-based systems to drive-in operations with large front-end loaders for block handling. Diamond wire saws also play a crucial role in slabbing. Traditional gang saws cut at a rate of only 3/4 inch per hour, taking days to process one block. In contrast, multi-wire diamond machines now achieve 12 to 14 inches per hour, slabbing a block in just hours. Further innovations include chainsaw-like quarry saws with diamond-segmented belts, improving both safety and productivity. Computer-assisted profiling systems now enable precise, automated shaping of stone with minimal manual intervention. These technological upgrades have dramatically increased efficiency, reduced labor, and lowered production costs, making formerly inaccessible stone economically viable to extract. Marble is extracted from the quarry using diamond wire saws, which cut large blocks from the rock face. These blocks are carefully detached and lifted for transport to the processing plant. At the plant, the blocks are sliced into slabs using gang saws and multi-wire saws. The slabs are then dried, treated with resin to fill natural pores, and polished for a smooth finish. After curing, the slabs are cut into tiles of desired dimensions. Final steps include edge finishing and quality inspection before packaging. The OSA Self-Loading Mixer X1100 is a compact and efficient solution for on-site concrete production. It automatically loads cement, stone, and sand, allowing operators to mix materials directly at the construction site. With a mixing capacity of 1.1 cubic meters per load, the process takes just a few minutes, providing fast and consistent batches. This self-contained unit eliminates the need for external mixing trucks, reducing transportation costs and lorry waiting times. Ideal for small to medium-sized projects, the X1100 increases productivity, lowers labor expenses, and delivers concrete exactly when and where it's needed, saving both time and money. FastPatch ACR Alligator Crack Repair is a cold-applied, 100% solids polymer composite used for restoring cracked asphalt surfaces. Designed for easy mixing and application, the material comes in ready-to-use kits requiring no water or solvents. It effectively fills and seals alligator cracks, creating a durable, water-resistant layer that helps prevent future damage. During application, the material can be spread using a squeegee to any desired thickness, depending on surface conditions. Its flexible formulation allows for excellent surface coverage and adaptation to irregularities, making it ideal for professional and DIY use in asphalt maintenance. A 53-meter-high chimney is demolished using a specialized long-reach demolition machine. The machine, equipped with a 50-meter arm, approaches the chimney and starts the process from the top. A hydraulic attachment precisely breaks the concrete structure into smaller pieces. The operator carefully maneuvers the arm to ensure accuracy and control, gradually reducing the height of the chimney section by section. Debris falls within a controlled area to prevent damage and ensure safety. The long-reach design allows the machine to remain at a safe distance while maintaining stability and reach. The demolition continues in a top-down sequence until the chimney is completely dismantled. Throughout the process, dust is minimized using water spray systems to maintain visibility and reduce environmental impact. The operator begins by engaging the hydraulic control lever to release the saddle lock. Gradually, the saddle swings outward from the machine's center line, rotating horizontally to reposition the mold board. This movement allows the mold board to extend further beyond the wheels. Once the desired offset is reached, the operator re-engages the lock mechanism, securing the saddle in place for precise grading near edges, ditches, or obstacles. The assembly process of the Terex Demag CC6800 crawler crane begins with preparing a compacted and leveled ground surface to support the crane's total weight and counterweight configuration. The crane, with a lifting capacity of 1,250 tons, is transported in components and assembled on-site. The undercarriage modules, equipped with dual crawler tracks, are positioned using transporters or smaller mobile cranes. These tracks provide the crane with both mobility and low ground pressure. The car body is then mounted onto the undercarriage, followed by the installation of the slewing ring and rotating superstructure. The backmast, which provides additional leverage and counterbalancing capability, is attached to the rear section of the superstructure. Counterweight slabs, each weighing several tons, are loaded onto the tray using auxiliary cranes and secured using locking mechanisms. The central ballast is mounted first, followed by the superstructure counterweight in a symmetrical layout to ensure balance during lifting operations. The main boom, composed of lattice sections, is assembled on the ground using pin connections. Hydraulic or strand jacking systems are then used to raise the boom to its working angle. The superlift mast and tray are connected if the lifting plan requires extended reach or capacity. Once the configuration is complete, typically including main boom, backmast, counterweights, and superlift if required, the crane undergoes functional testing. Control systems, including load moment indicators and boom angle sensors, are calibrated. This assembly process ensures structural integrity, load stability, and readiness for lifting critical oil and gas infrastructure components. The swage lining process is a trenchless pipe rehabilitation technique that involves installing a new polyethylene liner inside an old pipe without excavation. The procedure begins with the preparation of the site and inspection of the existing pipeline, which in this Berlin project was a heavily aged cast iron pipe over 80 years old. A pulling pit and receiving pit are established at both ends of the section to be rehabilitated. A PEHD pipe with a slightly oversized diameter, in this case 1,220 mm and 60 mm wall thickness, is prepared and aligned with the existing pipe. The pipe is then temporarily reduced in diameter using a specially designed die mounted in a swage lining machine. This die compresses the PE pipe to a smaller diameter as it is pulled through, allowing it to fit inside the host pipe. Using a hydraulic puller, the reduced PE pipe is drawn through the old pipeline. Pulling forces can reach 120 to 130 tons, especially when there are bends, corrosion, or obstructions inside the host pipe that cause additional friction. Once the liner reaches the full length, it is allowed to re-expand naturally, forming a tight mechanical fit against the inner wall of the old pipe. Following the insertion, end connections are made and the system is tested for integrity. The process concludes with final reconnection to the network and backfilling of the Precor offers a specialized range of tools for efficient installation of drip irrigation systems on polyethylene, PVC, and semi-rigid pipes. Key machines include the Eagle machine, designed for high-volume precision work, and the Gorilla machine, ideal for accurate perforation on semi-rigid pipes. The Mammoth perforator is built for large diameter pipes, while the B-connector perforator enables fast and accurate emitter installation. For unique applications, the Scorpion perforator and the Bear oval pipe perforator are engineered to handle oval and non-standard pipe shapes. Each tool is designed to minimize manual effort, reduce installation time, and ensure precision. Precor tools help irrigation professionals improve efficiency, avoid leakage issues, and lower long-term operating costs, making them essential for modern drip irrigation system setups. The piling rig begins by positioning itself on the designated hard terrain. Using hydraulic power, it deploys a rotary drilling system to bore into the ground. The rig applies a torque ranging from 150 kN/m to 600 kN/m to rotate the drilling tool, penetrating soil layers with diameters from 500 mm up to 3,500 mm. As drilling progresses, soil or rock is extracted continuously. The rig can achieve piling depths up to 135 meters. After reaching the required depth, reinforcement is inserted and concrete is poured to complete the bored pile. This process ensures stability and load-bearing capacity in tough geological conditions. The construction of the Olifants River Arch Bridge commenced with comprehensive geotechnical investigations, followed by foundation preparation on both banks of the Olifants River. Due to weathered rock formations, mass concrete blinding layers were poured, and high-capacity rock anchors were installed to enhance horizontal load resistance and foundation stability. Temporary structural steel trusses were then erected to support the self-weight of the in-situ concrete arch during construction. These trusses, weighing approximately 60 tons, were designed to slide laterally to support the symmetrical construction of the twin concrete arch ribs. The arch was cast in two halves using high-strength concrete in custom-designed formwork. The arch was pre-cambered by 85 mm to account for deflection. Pre-cambering was applied to each arch segment to counter deflection and ensure the correct final geometry after removal of supports. Once both arch halves were complete, the support trusses were moved into their second position using 95-ton hydraulic jacks, aided by graphite grease to reduce friction. The arch thus acted as a compression element in the final structure. The bridge deck was then constructed using a twin-box spine design. It spans continuously across the arch without intermediate joints, reducing long-term maintenance. The reinforced concrete deck is designed to handle live loads from highway traffic, including heavy trucks, in accordance with specifications. Its total length is approximately 125 meters, and the central span over the river is 90 meters. To reduce internal bending moments, concrete hinges were cast at the arch deck connections. These allow controlled rotation, improving durability and reducing stress concentrations. Reinforced piers transfer loads from the deck to the arch efficiently. Final works included installation of precast parapets, waterproofing, drainage, a downstream pedestrian walkway, and asphalt surfacing. The bridge now safely carries the N7 route, improving regional connectivity and demonstrating advanced South African bridge engineering.